Good evening, everyone. Welcome you all in the One Mark Solution this platform. And as you know, we are conducting regularly the subjective webinars for the 1 mark questions, 1 mark questions like multiple choice question, true, false, fill ups, and other type of 1 mark questions. So today we are going to discuss about the chapter 14 of physics, class 12. The name of the chapter is semiconductor electronics, devices, materials, etc. So today we have with us Madam Sanitha MM from Thrissur, Kerala. Madam, I would like to welcome you on this platform on behalf of all the viewers and on behalf of One Mark
Thank you.
Solution.
Thank you.
Uh, Madam is working as a PGT physics as well as HOD science in IES Public School, Thrissur, Kerala. Since last 22 years, she is teaching class 11th and 12th physics, and she has a very large experience in teaching field. Also, she is the in charge of Atal Thinking Lab in her school, and also she has conducted so many webinars, so many seminars, so many trainings for the CBSE teachers in the field of physics. So, Madam is definitely having a good experience in the field of physics, and also we hope today's session will be very good. Uh, as we are expecting from the of our resource persons that the students will be benefited from the expertise and the experience of the resource persons. So I would not take much time. I would like to request all the viewers who have not subscribed our channel yet, kindly subscribe the channel. Who are new today or who came first time on this platform, subscribe the channel, and definitely you can see the previous webinars also from the playlist of this channel. Madam Sanitha MM, hand over to you.
Thank you, sir. Thank you very much for giving an opportunity to discussing 1 marks in 1 mark solution. Now, good evening all once again. Now, we are going to start with the 14th chapter of 12th. Then actually it is not the last chapter. Last chapter is telecommunication, but it is now deleted. And in this chapter also, so many topics are deleted. So which all topics is there, that only we are going to discuss it. And semiconductor, as you know, that it's very, very important nowadays. Why? Because now in this pandemic situation, actually we are using technology, isn't it? Now also we could connect all together. That means I'm sitting in my home and connecting to all means what is that? Only because of these semiconductor devices. So that is why the technology has developed a lot, and only because of these electronic devices. So this is only a little bit only we are studying in 12th standard, and you will be studying more about in engineering also. So vast one. Now, what do you mean by electronics? We can say that it is actually controlling the flow of electrons, the direction of the flow of electrons. And these devices, we can say that it is a main building block of electronic circuit. And semiconductors, we can say, without any heating and large space also is not available, not needed for these semiconductor devices, of course. Now, one more specialty of this, we can say that it is low, they are consuming low power, and they will be operating at low voltage and long life and high reliability. And the very important thing is small in size. Why? Because it's very compact. Nowadays, you can see that it is very compact. Your mobile screen, your laptop, or anything, we can say within small screen, we can use this. Now we will go for detail about the semiconductor devices. Semiconductor, actually, we can say that semi means what is that? Electricity. It will be allowing only partially, we can say. So substance can be divided into three on the basis of resistivity or on the basis of conductivity. Now let us move on to detail about the semiconductor. The first question, you can see that the number of electrons in the valence shell of a semiconductor. Why the number of electrons we are asking? Why? Because semiconductors, a commonly semiconductor we are using it, germanium and silicon. In germanium and silicon, we can say that they are having valence electrons 4. that is tetravalent. Now you could say the answer for it. The answer is given as 1, 2, 3, 4. No doubt it is tetravalent. That means 4 only. That is the correct answer. So the number of electrons in the valence shell of a semiconductor, no doubt it is 4. Now we can go for the second question. Bonds in a semiconductor. Of course, we can say that they are 4 valence electrons, right? So it will be sharing with other atoms. That is, we can say that germanium and silicon is the most commonly used. We will take an example of germanium. Germanium, we can say that 4 valence electrons will be there. It will be sharing with neighboring atoms. So 4 valence electrons. Totally, we can say they will be completing octet. So which bond will be there sharing? Of course, you know that it is given as trivalent, covalent, bivalent, and monovalent. No doubt at all, we can say that sharing will be covalent bond. So in semiconductors, the bonds will be covalent. No doubt at all there. So the answer is B. Now let us move on to the next one, the resistivity of a semiconductor. I told that on the basis of the resistivity or conductivity only, we have divided the substance into semiconductors, conductors, and insulators. So let us see the resistivity of a semiconductor at room temperature. Room temperature, or usually we will take it as 27 degree, depends on the weather condition, we can say. Now, what is the value? The value, we can say, it is 10 raised to minus 3 to 10 raised to 6. That means its value is lying between that of conductors and insulators. So it is not so much and it is not so low. At room temperature only we are speaking. So the second option is the correct, 10 raised to minus 3 to 10 raised to 6. When you are clicking the option, you should know, you should have an idea about the other options also. You can just have a look. The first option is 10 raised to minus 2 to 10 raised to minus 5. Anyway, what is it? It is not the answer, it is very low. Then we will go for the C option, 10 raised to 6 to 10 raised to 10. That also, it is very high. Then the D also we can't take. Why? Because it is very high, 10 raised to 10 to 10 raised to 12. And you can see this one, ohm centimeter. Usually we will say resistivity in ohm meter. If it is ohm meter, the answer will be different. That means 1 meter, you know that it is 100 centimeter, right? Right? Now we can say that the option is B. The option 10 raised to minus 3 to 10 raised to 6 ohm centimeter. Now let us move on to the next question. That is at absolute zero. Absolute zero, you know that it is minus 273.16 Kelvin, we can say. Silicon, SI means silicon, acts as a. Why we are giving importance to silicon? Silicon and germanium, again I'm telling, silicon and germanium is a commonly used semiconductor. So it will act as a, whether it is semiconductor or insulator, or the question is like that. Why the question is like that? We can say that absolute zero, we can say that there is no free electron in silicon and germanium. Why it is like that? They are forming covalent bond, that is sharing. So this one silicon atom is in sharing with the other silicon atom, and they are having a covalent bond, means 8 will be completely. That means octet will be completed. So there is no free electrons, isn't it? Only absolute zero. When temperature increases, they are getting more energy and they will be breaking the bond and will be option, that is a correct one. Pauli's exclusion principle, and you know that no two electrons will be in the same shell, isn't it? And we can say that if any 4 electrons or any electrons, we can say the 4 quantum numbers will be there. So we are clicking on the Pauli's exclusion principle, and this question in the board exam also they have asked. So the option is Pauli's exclusion principle. Now we can go for the next question. That is energy band. Identify semiconductor from the given energy band diagram. I could say one sentence for energy band. What is energy band? You should know that, because in the basis of the energy band only, in this chapter, we are dividing the substance into three again: conductors, semiconductors, and insulators. So energy line diagram you have studied in atoms. That means for an isolated atom, each electron have discrete energy level. But if it is in a solid or a molecule, what we can say it, by the influence of the other atoms or the electrons, this energy level is divided into a large number of energy levels, and they are very, very, very closely packed. And this continuous energy levels, we can call it as energy band. Energy first, if it is in the first orbit, we can call it as first energy band. And if it is in the valence shell means outermost shell, we can call it as valence band. In some cases, we can see that the electrons are ready to contact. So we can call it as conduction electrons. If we can see that if they are ready to conduct, the energy of these conduction electrons, we can call it as conduction band. So two bands are there: valence band as well as conduction band. But there is a gap between these two bands. That is energy. Now you could see three band systems are there. We have to identify which one will give the semiconductor. You can see the first option, a gap will be more. That means from the valence band, electron have to jump to conduction band. That means so much energy is needed, right? Now we can say that second one, a small gap is there. In the third case, we can say already it is overlap. That means already electrons is there in the conduction band. So the first one, we can say there is no chance to conduct. So it is an insulator. And the third one, we can say already overlapping is there. So we can call it as conductors. Overlapping means there is no energy gap. And the second one, we can say semiconductors. So the answer is semiconductors. And one more thing I want to specify, that the energy gap of insulators is around 5 electron volt. And the energy gap of semiconductors, we can say around about 1 electron volt. But in your NCERT textbook, it is given as on the basis of 3 electron volt. If it is greater than 3, we can call it as insulators, and if it is less than 3, we can call it as semiconductors. And conductors, you know that there is no energy gap. Now let us move on to the next one. Next question is, carbon, silicon, and germanium have 4 valence electrons each. These are characterized by valence and conduction bands separated by energy band gap respectively equal to EgC, EgSi, and Eg germanium. Which of the following statement is true? So I should give the options. You can see the options. Anyway, we know that the energy gap of carbon is more. That is why we are not taking carbon into account for the semiconductor. We are not using carbon. In different forms we are using, but carbon as such we are not using, just like germanium and silicon. So we will just go through the options. We can say the first option is silicon is less than that of germanium. Germanium is less than that of carbon. That is not the correct answer. So we can go for second option also. We can see that carbon is very less. So no need to go for that. Now we'll go for the C, option C. Energy of carbon is greater than silicon is greater than germanium. That means I told that carbon is having very much high energy, almost we can say 5 electron volt. So what about silicon and germanium? We should have the value of the energy gap also. Silicon is having 1.1 electron volt and germanium is having 0.7 electron volt. So which one will be the answer? We don't want to go for D also. No doubt it is almost equal. No, it's not correct. So the answer we can say that the correct option we can say C, option C. Now let us move to the next one. Next question we can say NH and Ne. NH means number of holes and Ne means number of electrons, or we can call it as hole concentration and electronic concentration. Let NH and Ne be the number of holes and conduction electrons in an intrinsic semiconductor. Intrinsic semiconductor means pure semiconductor. If it is a pure semiconductor, the number of electrons and number of holes will be equal. Why? Because there is no free electrons to conduct. So that is why intrinsic semiconductor also will be acting as an insulator. Pure semiconductor, we can call it as intrinsic and it will act as an insulator. But when temperature increases, what will happen? When temperature increases, electrons will be breaking out from the covalent bond. If one electron is coming out of the covalent bond, what will happen? There will be a space there. There will be a space, and that space we can call it as holes. Actually, nothing will be there. We are calling it as holes, and the charge we are giving as positive charge. So in intrinsic semiconductor, if one hole is creating, one electron also will be there. So the number of holes and the number of electrons will be equal. Now you could find the answer from this. No doubt, the option, it will be B itself. Okay, NH is equal to Ne. Now things clear, answer B. Now we can go for the next one. Suppose a pure silicon crystal has 4 into 10 raised to 28 atoms meter raised to minus 3, that is per meter cube. It is doped by 1 ppm. 1 ppm means part per million concentration of pentavalent. Pentavalent means 5 valence electrons will be there. That is arsenic. Calculate the number of electrons and holes. Now, if we are adding a impurity to the germanium or silicon crystal, we can say that we can increase the conductivity. Now here we are adding arsenic, pentavalent. So the number of electrons will be more. Now we have to calculate the number of electrons and holes from the given data. So here the data is given as 4 into 10 raised to 28 atoms, but we have to multiply into 1 ppm. So we have to convert into 10 raised to minus 6. You can just convert it. 4 into 10 raised to 28, you have to multiply into 10 raised to minus 6. So you will get 4 into 10 raised to 22. But you should have an idea about the relation between Ni, NH and Ne. Already we have, just have a look into the intrinsic concentration. Ni is equal to NH is equal to Ne. So from this equation, we will get it. Ni squared is equal to NH into Ne. From this equation, we will get NH. NH is equal to Ni squared by Ne, we will get it. Now, Ni squared, we can say that 4 into 10 raised to 20, 4 into 10 raised to 28 into 10 raised to minus 6. So we'll get the answer 4 into 10 raised to 22. Ni here, it is 1.6 into 10 raised to 16. So we can just square it. You will get 2.56 into 10 raised to 32 divided by 4 into 10 raised to 22. So the answer, you will get it as the 6.4 into 10 raised to 9. So the answer will be B. Now we can go for, I think it's, the equation, I think it will be clear. And this equation is very, very important. Why? Because Ni, the question can be asked. This is a board question. Sometimes it will be asking in the board, and it is the example question in the NCERT textbook. Now we can go for the next question. Carbon, silicon, and germanium have 4 valence electrons each. That already we have specified it. At room temperature, which one of the following statement is most appropriate? So let us see the statement first. The first statement, the number of free conduction electrons is significant in C, but small in silicon and germanium. It won't be possible. That we know that free conduction electron is not possible in carbon. Why? Because the gap is very large. And the second option, the number of free conduction electron is negligibly small in all the 3. That is also not possible. And the option C, we can say number of free electrons for conduction is significant in all the 3. That is also not possible. And the last option, we can say that the number of free electrons for conduction is significant in silicon and germanium, and it is very, very small in carbon. electrons. We will see that it increases exponentially. One equation is there, is equal to e raised to minus Eg divided by 2 kBt. From that equation, that is exponential equation, we can say that from that equation, we will get it. The options, we will just read it out. Increases exponentially with increasing band gap. No doubt, it won't be possible. It won't be like that. We won't get the electrons now. The next option, decreasing exponentially with increasing band gap. When the gap is increasing, what will happen? It will be decreasing exponentially. That means it will be decreasing. So option B is the correct answer. And if you're going for C and D, it decreases with increasing of temperature. It won't be possible. And it is independent of the temperature and the band gap. So the answer is option, we can say B. Next, we can go for the next question. The impurity atoms with which pure silicon may be doped to make it a p-type semiconductor. Now, what do you mean by doping? We want to dope a semiconductor to increase the conductivity only. We have to increase the conductivity. So how will you increase the conductivity? By doping germanium or silicon. That means we have to dope with pentavalent or a trivalent. If you are doping with pentavalent, we will get n-type semiconductor. Why? Because penta means 5 valence electrons will be there. So if it is doped with the germanium with the 4 valence electrons, 1 electron will be free. So the number of electrons will be more in n-type semiconductor. So we can divide semiconductor into n-type and p-type. Together we can call it as extrinsic semiconductor. And in extrinsic semiconductor, one is n-type, the other one is p-type. How will you get p-type semiconductor? By adding trivalent impurity. Tri means 3 valence electrons only will be there. So 3 valence electrons, when it is adding, what will happen? There, one empty space will be there. Vacancy will be there. Then that vacancy, we can call it as holes. We will consider as positive. So we are termed as, but we are giving as p-type semiconductor. That type of semiconductor, we can call it as p-type semiconductor. And out of these 4 options, which one is the trivalent impurity? We can find it to get p-type semiconductor. Phosphorus, boron, antimony, nitrogen. Isn't it? So which one is the correct answer? We can say boron is the correct answer. Okay, when boron, that means trivalent, when it is added to p-type semiconductor, germanium or silicon crystal structure, we will get p-type semiconductor. Okay, next one we can go for a p-type semiconductor is the options which we will read it. Positively charged, negatively charged, uncharged at 0 Kelvin but charged at high temperature. Here this is very, very important one. Usually we will say p-type. P-type means what is it? Positive. But n-type it will be negative. No, it is wrong. How will you get p-type semiconductor? When we are adding a impurity. When we are adding an impurity, we will get p-type and n-type semiconductor. For example, if you are adding a trivalent impurity, that is a boron, if they are adding it, there creates a hole. That means they will accept electrons from the host atoms. So they will get more electrons. If they are getting, they will get negative charge, isn't it? And we can say that the host atom will get positive charge, and this, that means boron is getting negative charge. So positive and negative, put it together, we can say it is neutral. So if it is a p-type semiconductor or n-type semiconductor, we can say it is electrically neutral. This is very important. Usually the students will make a mistake for this. So the answer, it will be uncharged. That means neutral. Next, we can go for the electric conduction in a semiconductor takes place due to. In semiconductor, you know that electrons, 2 things we have discussed. What is it? Electrons and holes we have discussed. So surely we can say in semiconductor, the electric conduction takes place with holes and electrons. Not only electrons only, holes only, it is both electrons and holes. And this question not only have to study here, you have to study in current electricity also. That is the charge carriers in different substance, it is there. That is conductors, semiconductors, ionized gas, like that. So here the answer is holes only. Now let us move to the next one. The strength of the semiconductor crystal comes from where we are getting the strength, we can say. Of course, we will just go through the options. Forces between nuclei. No, of course. Why? Because it is nuclear force. Forces between protons. No, it is electrostatic force. Yes. The next one we can say electron pair bond. That is the strength of a semiconductor. We know that. Electrons, they are sharing and the bond is there. That is a covalent bond. Due to this electron pair bonds only, the semiconductor, this much strength is there. Next, we can go for in good conductors of electricity, the type of bonding that exists. Actually, we are dealing with the semiconductors. Then why good conductors of electricity? Why? Because what is it? Why? Because, sorry. Why? Because conductors, first thing is conductors, then only will come under semiconductors. So in good conductors of electricity, the type of bonding, we can say, we can just go through the options and we can find it. Van der Waals, covalent, ionic, metallic. No doubt at all, it is metallic. Why? Because metals we can say that it is good conductor. So the answer is metallic conductor. That is metallic bond. Now we can go for the next question. This is a simple problem. For a PN junction, the average value of a potential well means what is it? You know that, isn't it? Is 0.1 voltage and the electric field is 10 raised to 5 volt per meter. Is present at junction region. What will be the width of the depletion layer for this junction? So here, what all things are given? What all data are given here? The data is given is the first one we can say potential. Potential is 0.1 voltage. So let us write V is equal to 0.1 voltage. And the electric field is equal to 10 raised to 5 volt per meter. So what is the relation between electric field and the potential that you are studying in the second chapter? You are getting from the second chapter. That is E is equal to V by D. This very important equation. You are studying the equation in this manner. E is equal to minus dV by dr. That is, electric field is the negative potential gradient. So this equation is very, very important. The relation between voltage and the electric field or potential and the electric field. Now the question is, here it is, what will be the width of the depletion region for this junction? What is the depletion region? When two types of semiconductors, that is p-type and n-type semiconductor, join together. We can't join as such. In one semiconductor itself, we are doping one side trivalent and one side pentavalent. We will get PN junction formation, and that is very, very important. In this PN junction formation, we can say that at first diffusion of electrons takes place. After that, drift also takes place. So both drift and diffusion takes place. After some time, a junction will be formed at the center. That junction we can call it as depletion junction, or simply we can say PN junction. And the depletion region, the thickness of the depletion region is 1 by 10 raised to 6, that 10 raised to minus 6, that is 10 raised to minus 7 meter is what is the thickness of the depletion region. And you can think of how small it is. And diode also, you have seen it's very small. In that only the depletion region is very small. Depletion region is having some potential, and this potential we can call it as barrier potential also. Here, the question is asking what is the width of the depletion layer from this data is given. So, E is equal to V by D. D is the width of the depletion region, we can say. So, V is given as 0.1 and E is given as 10 raised to 5. So, when you are doing it, that means D is equal to V by E. V is 0.1 voltage and E is 10 raised to 5 voltage. So 10 raised to 5 will go up. 10 raised to 5 will go up. So 10 raised to minus 5. 10 raised to minus 5 into 0.1, we can say 10 raised to minus 6. So the answer will be 10 raised to minus 6 meter. That is the answer. Answer A. Now let us move to the next question. In the circuit shown, if current for the diode is 20 microampere, the potential difference across the diode is. You can see a picture there, a circuit diagram with a diode and a cell and a resistance. It is connected in series only. For doing this, you should know forward and reverse biasing. When P is connected, P means P-type semiconductor is connected to the positive of the cell and N-type is connected to the negative of the cell. We'll call it as forward biasing. If it is in the reverse manner, we'll call it as reverse biasing. In forward biasing, we can say it will conduct. But in reverse biasing, diode will not conduct. So here you can see the negative is connected to positive of this. Why? Because the symbol of this diode, you can see that negative and positive. So it is connected to the positive only. So it is reverse bias. So what will be the potential difference across the diode? Means the same voltage what we are giving it. What is the voltage we are giving? 4 voltage. So only that voltage we are getting. So the answer is 4 voltage. Even though resistance is also there, it is not taking into account. And that is very important also. You should know that which biasing first of all. Next, we can say region without free electrons and holes in a PN junction. Region without free electrons and holes in a PN junction. Which is the region we have to find? Is it N region or P region or depletion region and none of this? Actually, there is no, if the PN junction is formed, there won't be no electrons or holes will cross. So that we can say that is why we can call it as barrier potential. It is barrier, right? That means it won't be crossing holes and electrons through this junction. So in the depletion region, there won't be no free. Free means there is no movement. Immobile charges. We can call it as immobile charges. It is devoid of immobile charges and holes, electrons and holes. So the answer is no doubt it is depletion region. Next, we can go for the next question. In PN junction, the barrier potential offers resistance. Barrier potential told that potential which is preventing the flow of electrons and holes. So we'll see the options there. In PN junction, the barrier potential offers resistance to the first one, only free electrons in N region, and the second one, only holes in P region. We'll see that which is the option. In N region, only free electrons. N region, we know that, isn't it? Which is the majority carriers. And in P region, we know that majority carriers are holes. But here we can say resistance. They are just giving a barrier to majority carriers or minority carriers. Actually, they are giving barrier to majority carriers. That means both in the N region and in the P region, majority carriers, we can say electrons, they will block it. Next, we can go for the next question. Which one of the following represent forward bias diode? That means forward biasing. Two biasing, we have already discussed about the forward and reverse biasing. Forward biasing is P is connected to positive and N is connected to negative. If it is reverse, reverse means P is connected to negative and N is connected to positive. That is reverse biasing. So we will see the circuits. Yes. And this is very important. Actually, it's very simple, but you should know what is the difference between -4 and -3. Here, you can see that the positive is connected to the -4. And the negative is connected to -3, that is -3 voltage. So is it forward or reverse biasing? We can say that it is reverse. Why? Because here you can say that -3 is connected to negative and the -4 is connected to positive. And the second option we can say -2 and +2 voltage equal, not equal, only the negative and positive is not. It's connected, and the positive, that means it's the plain part, we can say positive, it is connected to negative, and the line we can say it is negative is connected to positive. No way it is reverse biasing. And what about the third one? Third one, we can say positive is connected to 3 voltage and negative is connected not to negative, it is 5 voltage. If it is less than 3 voltage, we can consider that also forward bias. That you have to keep it in mind. If it is that negative is connected to 2 voltage or 1 voltage or 0 voltage, we can consider as forward biasing. But here, the last one, what is the last one? We can say 0 voltage and negative voltage. So that is the correct answer. Positive is connected to positive. It's not positive, actually 0, but compared to negative voltage, compared to -2 voltage, 0 is positive. So that is why here we can say answer is the last option, that is 4. Next, we can go for, yes, you can see 3 graphical representation. 3 graphical representation. The first one, we can say different colors. So you could understand that what is different colors. And the next one is, what is it? Reverse biasing. And yes, reverse and forward is also there. The next one is reverse biasing. So question, we will see the question, right? The IV characteristics of an LED. The IV characteristics of an LED. LED means light emitting diode. In this chapter, you have to study 3 diodes, 3 optoelectronic devices, we can call it as. 3 optoelectronic. Opto means something related to light. So here LED means light emitting diode. The second one you have to study is photodiode. Photo means light, something related to that. And the last one is solar cell. Of course, we know that solar cell, it is working only because of the solar energy. So in this characteristics, which is the correct option, we can see. Anyway, it won't be working in the reverse biasing. LED will work only on the forward biasing. So the answer will be A option. And one more thing, we can see that different colors we will get. How will you get different colors in LED? Depends on the component we are using. Gallium arsenide phosphate, gallium arsenide, like that depends on the colors, depends on the component of the LED, we will get different colors. So the option is A, the first option. The characteristics, VI characteristics. What do you mean by VI characteristics? Actually, we can say gives a relation between the voltage and the current. Now we can go for the next question. Identify the semiconductor diode whose VI characteristics is as shown. Semiconductor, we have to identify. Characteristics is given there. VI characteristics is given. We have to identify the diode used here. It is in reverse biasing. And you can see 4 graphs, isn't it? I1, I2, I3, I4. So, and it is given there, I4 is greater than, I3 is greater than, I2 is greater than I1. What is this? I is intensity, the intensity of light. So, what is intensity? How we are getting the light also? Here we can say that in photodiode, we will discuss about the photodiode. LED already we have discussed. Photodiode, when light, we can say that it is in reverse biasing. Photodiode always connected in reverse biasing. Here also we can say that it is connected in, the graph is reverse biasing. So it can be reverse biased only. That means it can be photodiode only. Now, what is the function of how it works? The photodiode works, we can say. When it is in forward bias, electrons and holes will combine together at the junction. Okay, so the light will be emitted there. So we can see that, we can say that what is the answer here? Light emitting diode, photodiode, and solar cell, we can say Zener diode. So the answer is photodiode only. Answer is B. The answer will be B, that is photodiode. Next, we can go for the next question. A PN junction is fabricated from a semiconductor with a gap of 3 electron volt. The wavelength of the radiation which can it detect. 3 electron volt is fabricated, means it is incident on the diode. The wavelength of the radiation it can detect. In which wavelength it can be detected. The equation we are using here, it is equal to h nu. That already you are studying in chemistry, physics also a number of times you are studying, is equal to h nu. Nu is C by lambda, hc by lambda we can say. Energy is 3 electron volt and the lambda is given here. Here using the equation is equal to hc by lambda. Lambda, first we can, if we are substituting for 600 nanometer, H is the Planck's constant, 6.6 into 10 raised to minus 34, and C is 3 into 10 raised to 8 meter per second. If you are substituting, you will get 600 nanometer. If you are substituting, we won't get the energy gap 3 electron volt. So when you are substituting 400 nanometer, we will get this. That means they will detect this wavelength only. Second option. So no need of going for the C and the D option. Now we can go for the next question. In a half-wave rectifier circuit, what is the use of diode? That is the next thing we have to go for. Rectification. Rectification means we have to convert AC into DC. That means we don't want the negative half cycle, only one cycle we need it. That is why rectifier. Two types of rectification is there, half wave and full wave rectifier circuit. In half wave rectifier circuit, operating from 50 Hertz main frequency, the fundamental frequency in the ripple factor, the value of the ripple factor for half wave is almost 1.21. We will take it as 1. For easy calculation, we will take it as 1. So if you are giving 50 Hertz from the main frequency, what will be the fundamental frequency in the ripple? No doubt it will be same. Why? Because the ripple we are taking it as 1. If it is, we are taking 1.21, some changes will be there, but the option it is not there. So the answer we will get it as 50. If when you are doing MCQ, you can use this trick also. That means you can just go through the options and which one is more accurate from the equation, you just click for that. That is the 50 Hertz. 1.21 is the ripple factor that you have noted. Here we will take it as 1 only. So the answer is B, that is 50 Hertz. Next, dominant mechanism for motion of the charge carriers in forward and the reverse biased silicon PN junction are. We will see the mechanism. What is the mechanism? First, we will see the options and we will say the answer for it. The first option is the drift in forward bias, diffusion in reverse biased. Diffusion means it is going through the junction. And drift, we can say when we are applying electric field, the velocity of the electrons, we will call it as drift. That is why drift and diffusion is very important. So the first option, drift in forward bias, no. Diffusion in reverse bias, no. We will just reverse it. We will see that in this mechanism, that means in the motion of the charge carriers, we will take diffusion in forward bias and drift will be in reverse bias. So no need to go for the next options. Why? Because in the next C and D, we can say diffusion in both forward and reverse bias, not at all possible. And the next one, drift in both forward and reverse bias, there also it's not possible. So the answer we can say it is B, that is diffusion in forward and drift in reverse biased. Now we'll go for the next question. Let NH and Ne be the number of holes and conduction electrons in an extrinsic semiconductor. This we have come across in intrinsic semiconductor. If it is intrinsic, we know that both are same. But here, we can say it is extrinsic, either P-type or N-type semiconductor. If it is written P-type, we can say majority carriers are holes. If it is N-type, we can say majority carriers are electrons. More electrons will be there. But here only extrinsic semiconductor is written. So the answer, the correct option, we can say it is not equal. Anyway, holes and electrons are not equal in extrinsic semiconductor. So the answer is D, option D. Next, we can go for a graphical representation. Again, we can say the graph shown in the figure represents a plot of current versus voltage. That is VI graph only. For a given semiconductor, we have to identify the region, if any, over which the conductor has a negative resistance. We will get resistance from the VI graph. Here VI graph is there and the slope of the graph gives the resistance. In this graph, we want to identify the negative resistance. That means when voltage is increasing, if I is decreasing, we can say that region will be having the negative resistance. So it is very clear that it will be, yes, we can just go through the options A, BC, AC, ABC. So the answer is no doubt it is decreasing only in the region BC. ABC is also there, but in that A is also coming. That is why that option we don't want to take. And the third option is AC. From A to C, it is not changing in that manner. And the first option is A. That also is not possible. So the correct option we can say BC, that is, it shows negative resistance. So the answer is the option B. Next, we can go for the circuit has two oppositely connected ideal diodes in parallel. That means diodes are connected in parallel. What is the current flowing in the circuit? You can see the diagram here. Two diodes are there and it is connected in parallel. Parallel, you know that what do you mean by parallel? That is common potential will be there. But you can see that the first diode D1 positive is connected to 12 voltage positive. Negative is connected to negative of the 12 voltage. So it is forward biasing. Forward biasing, the diode starts conducting. So we will take into account D1. What about D2? D2 we will see that line will be there. That is negative. Negative is connected to positive and positive is connected to negative. It will be reverse biasing. So it does not conduct at all. So we don't want to take D2 and the resistance along with it. You just avoid that. Now we have to find the current. With the usual formula. I is equal to V by R. From Ohm's law, we will get I is equal to V by R. What is V here? It is 12 voltage is given. Resistance, you have to find it from this combination. 3 and 4 ohm. It is connected in series. So 3 plus 4, we will get it as 7. So 12 divided by 7, you will get the answer. We can see the option 2, 1.33 and 1.73. The answer will be 1.73 ampere. That is option C. So see the circuit connected. If any diodes are connected, don't add all these diodes. You have to see that whether it is forward and reverse. It is not just like resistance. If the resistance are connected, we have to take into account. But diodes, if it is connected, we have to see that whether it is forward and reverse. If it is forward, we have to take into account. If it is reverse, no need. Why? Because the current is not flowing through this diode. Next, we can go for one more question like this. Process of, fill in the blanks like that. Anyway, it is multiple choice questions only. The process of converting alternating current into direct current. What is alternating? Changing current. We are getting in household appliances, we are getting alternate current only. That means 50 hertz. In India, we are getting 50 hertz and in America, we can say 60 hertz. That means it's very fast. So here, how will you convert? In our appliances, we need direct current. So how will you convert alternating into direct current is very, very important. And what is that process? We can call it as filtration, rectification, transformation, modulation. And the correct answer is we have to rectify the other part of the cycle. So the answer is rectification. So the process of converting alternating current into direct current, we can call it as rectification. The answer is B. Next, we can go for the output from a full wave rectifier. Half wave rectifier, we have seen it. That means only half wave will get it. If it is a half wave, it won't work fully. The device won't work. So that is why we have gone for the full wave rectifier. With the 2 diodes, we will get full wave rectifier, or with the 4 diodes also we can get this full wave rectifier. If it is full 4 diode, we can call it as bridge wave rectifier. Now you can see the output from a full wave rectifier. We can see the options. What is it? A pulsating unidirectional voltage. Pulsating means it is changing. If it is changing again, it is of no use. And we'll go for the second option, a DC voltage. DC means direct voltage. If we have to get it direct voltage, whether we are getting direct voltage, we have to see. And the C is 0. It is, what is it? 0 means anyway output is 0. It won't be the correct answer. So the correct answer we can say it is unidirection. That means one direction only, having small ripples. That also we can avoid with filter circuit. After the output of the full wave rectifier, we are allowing pass through the filter circuit. So it will be filtered and full DC we are getting, full direct current we are getting it. Next one, we can say, what is the resistivity of a pure semiconductor at absolute zero? We have come across at room temperature, what is the resistivity? 10 raised to minus 3 to 10 raised to 6 ohm centimeter, we got it. But here the answer is different. Why? Because the question is at absolute zero, what is the resistivity? 0, infinity, same as that of conductors at room temperature, same as that of insulators at room temperature. What could be the answer? We can think it of. 0. No. Resistivity is not 0. Why? Because if resistivity is 0, conductivity will be more. And we have discussed that at absolute 0, that is minus 273.16 Kelvin, it won't conduct. That means conductivity is 0. The reciprocal of conductivity, we can say that resistivity. So reciprocal of conductivity, resistivity. So what will be the answer? Answer will be, no doubt, it is infinite. Infinity is the answer. You can see that the electrical answer is given in detail. Electrical conductivity of a semiconductor 0 Kelvin is 0. So the reciprocal of that is infinity. So the answer is B. Next, we can go for the next question. Identify the device which is having the given output waveform. One waveform, we can see that. We have to identify which is the device. Two waveforms you have to study in this chapter. That is half wave and full wave rectifier. So we will see that which is that ripple. Here you can say with the dotted lines, you can see dotted lines is at the bottom. That is not taking into account only the solid lines. That means output we are getting. But full wave we are not getting. Only half wave we are getting. So this rectifier will be, no doubt it will be half wave. But one more thing it is asked, what is the ripple factor? Already half wave, for half wave rectifier, the ripple factor, I have mentioned it is 1.21. For a problem, we have done it, but I have taken as 1 there because for easy calculation. So the answer will be option A only, half wave rectifier with ripple factor 1.21. Yes, next. One serious drawback of semiconductor devices. Anyway, semiconductor also having advantage and disadvantage, but because of the semiconductor only, the technology, I told the technology is developed now. But one serious drawback is also there. Why? Because in germanium, we know that germanium, the barrier potential is 0.3 voltage and silicon is 0.7 voltage. That means it is working only with very low voltages. So what is the serious drawback of semiconductor devices? Now we will get it from there. They do not last for long time. No, it will. They are costly. No, it is not so much costly. They cannot be used with high voltage. Yes, absolutely correct. The C is the option. That is, they cannot be used with high voltage. And we will go for the last also. They pollute the environment. How come? They are not polluting. Electronics is not polluting the environment. So the option is, the correct option is C. They cannot be used with high voltage. Let us move to the next question. Efficiency of full wave rectifier. What is the efficiency of full wave rectifier? Efficiency of half wave rectifier, we can say 40.6%. Half means 50%. But we are not getting even 50. We are getting only 40.6. So what could be the efficiency of full wave? Double of it. So what is the double of it? 40.6. Yes, the answer will be, it is there in the option. 81.2%. Answer is B. Now we'll go for one word answer. The gap between the top of the valence band and bottom of the conduction band. That means valence band and conduction band, we know that. Below the bottom it will be valence band and top it will be conduction band. What is this gap? We can call it as forbidden energy gap, or simply we can call it as energy gap, energy band gap. Depends on this energy gap only we are divided into conductors, insulators and semiconductors. Next question. Why are silicon and gallium arsenide, GaAs is gallium arsenide, are preferred materials for solar cells? Only because of absorption, high absorption coefficient, we can say. You can see the figure also here. They are giving the energy and the solar irradiance intensity is also given. And it is very important in the board exam also they have asked, it is, if it is a 2-mark question, we have to, in detail, we have to write it. If it is a 1-mark question, you have to write this answer due to higher absorption coefficient. What do you mean by that? Means what all energy, what all light is incident, solar energy, or what all light is incident on this cell or incident on this diode, they will absorb it. So absorption coefficient is more in silicon and gallium arsenide, and of course the band gap also very less. So that is why we are preferring these for solar cell. Write the two processes that takes place in the formation of a PN junction, and that is very, very important. 1-mark question can be asked. Two process already mentioned it, diffusion and drift current, and that is very, very important also. Diffusion and the diffusion first take place, and after that drift, and after that only PN junction is formed. Next one. Why should photodiode be operated at a reverse bias? This question also can be asked for 2-mark question. So here we are discussing only 1 mark, that is the fractional change in why the photodiode is reverse biased. Fractional change in minority charge carriers is more than in the major fractional change in majority. That is delta P by P. Delta P means change. Fractional change means the change in P divided by the original one. Delta P by P and delta N by N. That is fractional change in minority will be more than the fractional change in majority when it is saturated. Reverse saturation current. That is why we are using it is in reverse bias. And if it is a 2-mark question, we have to write what is delta P, what is P, like that we have to explain it. Next one, we can go for what happens to the width of the depletion layer of a PN junction when it is forward and reverse bias. The question is very simple, but the question a number of times in the board exam they have asked, what happens to the width of the depletion layer of a PN junction? Junction, I told it's very small. It is 10 raised to minus 7 meter. When it is forward bias, what is happening? The junction will be reducing, and after that it will go off. Now the current will be passing through it. Now what is happening in the reverse bias? Reverse bias junction will be increasing like that. That means the voltages are adding up. So it is increasing. That is why it does not conduct in the reverse bias. So the answer will be in the forward bias, junction is decreasing, and in the reverse bias, junction is increasing. Now let us move to the next one. Assertion and the reason based. So first of all, we will see the assertion and reason. What is it actually? So 5 options are here. If both assertion and reason are true, and the reason is the correct explanation of the assertion, and the second one we can say both are true, but reason is not the explanation of the assertion. And the C option we can say one is true, that is assertion is true, but reason is false. And the fourth option we can say assertion and reason both are false. And E option is if assertion is false but reason is true. First you thoroughly go through this one. Then only you can answer for the question given. The question given is, we will see the question. Assertion, electron has higher mobility than hole in a semiconductor. No doubt at all. Why? Because electron will be moving very fast, isn't it? Then we can say reason. What is the reason given for that? Mass of electron is less than that of mass of hole. Yes. Mass of electron, we can say 9.1 into 10 raised to minus 31 kilogram. And the positive, we can consider hole as a positive. And if it is positive, we can say 1.6 into 10 raised to minus 27 kilograms. So mass of electron will be very small. So the answer, the option for the answer, we can say the first option. If the both assertion and reason are true, and the reason is the correct explanation of the assertion. So the answer, it is A only. Next, we can go for the second question of this pattern. Assertion. Silicon is preferred over germanium for making semiconductor devices. And the reason is the energy gap for germanium is more than that the energy gap of silicon. No, not at all. We know that, isn't it? Silicon is having more energy gap. So what will be the answer? The explanation, the reason is not correct. Assertion and reason is true, but reason is not correct explanation for assertion. So the answer is C, option C. And the last question of the assertion, we can say this pattern, the crystalline solids have a sharp melting point. What is the reason behind it? All the bonds between atoms or molecules of a crystalline solids are equally strong that they get broken at the same temperature. They are getting broken at the same temperature. So, is it correct or not? Yes, of course. Why? Because if they are breaking at the same temperature, the melting point will be sharp. So, the answer is A. And we can go for the last question. State whether the given statement is true or false. And it is very simple question. The majority charge carriers in p-type semiconductor are electrons. Is it true or false? No doubt at all. You know the answer. It is false. If the question is majority carriers in n-type semiconductor electrons, it will be true. So that's all. Thank you.
Thank you so much, Sanita ma'am. You have explained very well this chapter, that is semiconductor electronics, and definitely our students who have attended this webinar session and who will see in future this video, because this video will be available on YouTube also. You can also refer to your students in future. So definitely they are going to be benefited from this chapter, and definitely they will get good marks from this chapter, because you have explained all the content very well. And I'm sharing the feedback link in the live chat box. Students are requested kindly fill the feedback forms and put the correct email ID, so that they can get the printable certificate if they will secure the 40% marks. That means 4 question correct out of 10 questions. 10 questions are there in the feedback form. So you can fill the feedback form and can get a very good printable certificate, and kindly join us on the upcoming webinars. Very soon we have going to connect the other chapters of physics, and as well as on 23rd we have the chemistry webinar. Likewise, we are conducting webinars from the other classes also, from class 6 to class 12. So kindly share about this channel with your friends, with your juniors, with your classmates also. And I would like to thank Sanita ma'am for being with us, for accepting our invitation, and
Yes.
helping students willingly, voluntarily. This platform is purely volunteer, and teachers are coming here and discussing the content for the students. And definitely, on behalf of One Mark Solution, on behalf of all the students, I would like to thank again Madam Sanita MM, and hope in future you will also join us for the other chapters.
Sure, sir.
Thank you so much. Thank you, one and all.
Thank you, sir. Thank you, sir.